There's something weird going on at the North Pole of Uranus. NASA's infrared maps of the planet show that the poles emit heat in a way that is completely different from the equator. And it might have more to do with Uranus's peculiar tilt than we thought. I'm here with Minute Earth. When NASA's Voyager probes flew by Uranus in the 1980s, they revealed that the planet's axis was tilted on its side relative to the Sun, almost perpendicular to the usual pole-on or pole-facing the Sun orientation that we see for most planets. We don't know exactly why this happened. Maybe something huge has crashed into Uranus in the past. But because of this unusual tilt, about half of Uranus experiences extreme cold while the other half is bathed in perpetual sunlight. But just how much heat is escaping from Uranus's poles has been a mystery since Voyager. It is not like we could just set up a thermometer on the North Pole of a faraway ice giant to find out. And without being able to measure the temperature directly, scientists have had a hard time figuring out what's driving the heat. One leading hypothesis was that the atmosphere at the poles was circulating in such a way that warmer, sunlit gases were mixing with the colder gases at the poles, raising the overall temperature there. Now, thanks to some infrared maps from NASA's Spitze Space Telescope, we have evidence of what's really happening. Spitze can detect heat because it observes in the infrared range of light, which is emitted by objects that are warmer than the cold space background. In 2010, researchers used the telescope to produce the first map of Uranus's global heat budget. They found that the planet's equator was emitting more heat than expected based on its temperature alone. This implied that something was transporting heat from the sunlit middle latitudes to the poles, which are closer to the star. But when the team looked closely at the poles, they found that the North Pole was actually emitting less heat than expected given its temperature, not more. The reason for this wasn't clear, but one idea was that the atmosphere at the poles was instead sinking rather than rising. If the heat from the atmosphere came from the sun, then sinking air would pull cooler gases from higher in the atmosphere down to the surface, lowering the temperature. So to get to the bottom of this, researchers turned to computer models of Uranus's atmosphere. They developed a simulation that took into account the planet's unusual tilt, its distance from the sun, and the amount of energy the atmosphere would absorb from sunlight. Then they compared the model's predictions about the heat budget to the observations from Spitze, and one set of simulated maps matched the data really well, thanks to the presence of two powerful jet streams at the poles, which they had added to the model to represent what they hypothesized was happening. These fast-flowing bands of air circle the poles in opposite directions, like the jet streams that encircle Earth. But unlike our jet streams, which are confined to the northern hemisphere and southern hemisphere, these hypothetical Uranus jets would be confined to the poles themselves. In this simulation, warm air from lower latitudes rises up to the poles and is then carried rapidly around the pole by the jet streams before sinking back down to the surface on the far side of the planet. And because the air is moving so quickly, it doesn't have time to cool off. So the heat that is released when it condenses is higher up in the atmosphere, where it radiates into space. This explanation makes sense of both the heat maps and the temperatures that the Voyager probes measured in the upper atmosphere. A paper describing the findings was published last month in the Journal of Geophysical Research. And the authors think that the pole-circling currents may even play a role in Uranus's bizarre tilt. You see, planets like Uranus and Neptune are thought to have formed in disks of spinning gas and gravity, probably after a large star nearby went supernova and left a bunch of angular momentum behind. Angular momentum is kind of like a quantity of spin. It's conserved, meaning that if no outside forces are acting on a system, the overall angular momentum stays constant. When there's an increase in angular momentum in one part of a system, there needs to be a decrease somewhere else. And over time, Uranus's atmosphere will transport angular momentum from the equator to the poles through these types of atmospheric motions. As the poles become more massive and therefore more massive, their gravitational pull will also increase. Eventually, it could become strong enough to pull Uranus upright again. That's just one possibility, though, and right now it is still unclear what keeps Uranus' poles so warm or what drives the jets that circle them. Spitze unfortunately stopped operating in 2020, so we won't be getting any more maps anytime soon. But the James Webb Space Telescope should be able to image Uranus in the next few years. If it can detect features as small as the poles of Uranus, it could look for signs of the jets in the new data. Either way, astronomers have learned a lot about the mysterious ice giants since Voyager flew by, and it shows us just how much more there is to learn about the solar system we call home. Thanks for watching this episode of SCI Show Space, and thank you to all of our patrons for making it possible for us to explore the Polar Atmosphere Oddity and everything else out there in the universe. And if you'd like to be involved in supporting the creation of fun science and text stories, you can check out our support page.